Yes, right, ranges. Who uses ranges all the time, uses ranges a lot in their code? Just, actually, that's I don't know, 10 hands or so? Who's kind of tried out ranges, you know, had a look at it, evaluated it, and gone, oh, maybe it's not for me? Be honest, I'm not going to be offended. Yeah, a few people. And who would like to see faster, safer, better ranges? Excellent. That's the bit you were supposed to vote for, so that's good. So ranges, yeah, they were one of their really headline features in C++20. You know, a lot of big things came along in C++20. Ranges were one of the big headline features. A lot of people, including me, gave talks, you know, before C++20 about the ranges features we were going to get. And there have been quite a few talks about ranges since C++20 as well. And I don't know about you, I watch a lot of conference talks. I'm particularly interested in ranges, so I watch pretty much all the conference talks that people give about ranges, and I've started to notice a bit of a pattern developing in these talks. So here's what I mean. So here's a talk from CPPCon. I think this is 2020. This is from Jonathan Bucara talking about his alternative ranges library that he calls pipes. 2021, here's Barry Revstin talking about his alternative ranges library he calls rivers. 2022, Arnold Schoedel talking about ThinkCell's alternative ranges library. We've already mentioned me, 2023, at this very meetup talking about my alternative ranges library. How many do you think we've got? Here's Google. They didn't want to be outdone by me. Here's Google at C++ Now 2024 talking about their alternative ranges library called Repel. Daisy Holman's alternative ranges library, the neatly named Daisy Chains from CPPCon 2024. And just from earlier this year, Joaquin Lopez talking about his alternative ranges library. So what did we learn from this? What does this tell us? With so many people are giving talks with very, very similar themes. Well, here's what I think. I think it tells us that people really like the features that ranges brings. They really want the functionality that ranges offers, right? This idea of being able to create these data pipelines, like you can do in a lot of other languages, is really appealing, really powerful. I call it sequence-orientated programming, right? This idea of just taking a sequence of values, maybe you filter, maybe you transform, maybe you know, whatever you do to it in this pipeline style. But the feature that we ended up getting has one or two problems in terms of safety, in terms of performance, in terms of ease of use. I think it's fair to say. And at least in my opinion, these kind of largely stem from the underlying iterator model that ranges uses. Okay, so if you've seen some of these talks, all of these, yes, hello.
Can you elaborate what you mean with safety or what the problem is there?
I will give you an example in just about 5 minutes. So the problems, at least in my opinion, largely stem from the underlying iterator model that ranges uses. Okay, the same iterator model we've had basically since 1998. So all of these talks, if you've seen these talks, they kind of all follow the same pattern, and I don't want to break with tradition. We're going to follow the same pattern tonight as well, because they start off and they show you a few examples of some problematic ranges code, and then they present the thing, you know, that is better. And there's a good reason for this, is because, you know, we want to highlight why you should care about the new library. So we're going to do that, but I'm not going to spend too long on the problematic ranges examples, because as I've just seen, there are plenty of talks out there that you can go and, if you want to find lots more problematic examples, or apparently listen to Nico's talk from this meetup last year. Okay, so we're just going to have a look at two issues, a performance issue and a safety issue. So performance, first of all. Here's what I want to do. I want to take a vector of integers and I want to print all of the even values, okay? pretty simple, hopefully. So here's how we can do it. We iterate over the vector. If the integer is even, we print it. Okay? But this is kind of old and boring, right? We want to use the new fun stuff. We want to use ranges, so we change this to use the filter view instead. Okay, so we set up our filter view, we iterate over the filter view, and we print all of the filtered elements. Okay? Look reasonable to you? Good. All right, so what we're going to do now is we're going to kind of behave like the compiler. We're going to start inlining functions, unrolling stuff, and trying to see what the compiler sees when we write this code. Okay? So the first thing we can do is we can desugar the range for loop. So the range for loop, it uses iterators behind the scenes. We can expand it out. It's roughly like this. This is slightly simplified, but it's basically this. So what we do is we call begin and end on the view object, and then and this gives us a pair of iterators, and then while the iterator is not equal to the end position, we print the elements, and then we print the element, and then we advance the iterator. Okay, so pretty straightforward. But now let's think about what the filter view has to do, because classic STL iterators, they begin what we call on track. That is, they need to have a value right there immediately available for you to get, right? If you call like vec.begin, and as long as it's not equal to the end position, you can immediately call operator star on it and get the first value. Okay? And if you think about what this means for the filter view, it means that when we call view.begin on the filter view, we need to do some work. We need to go and find the first element of the underlying vector that satisfies the filter predicate, in this case, the first even value. Okay? We need to go and find the first value that matches the predicate, that is, find if. And again, when we increment the view iterator, we call operator plus plus, we've got to do the same thing. Right? We've got to look ahead through our underlying vector, skipping elements until we find one that matches the predicate. And again, that's find if. And actually, if you go and look in the standard, it literally is specified to use find if. Okay, so we substitute in a couple of calls to find if, and it looks like this. And then we can just go and look up the definition of find if from the standard, and we can go and substitute that in. Okay, so we can substitute it in the first position, so that's to find the first element, and then for the increment, we can substitute it in there. And this is roughly what the compiler sees when we use a filter view, right? And I don't know about you, but this is a lot more code than I would expect, because we've got one loop to go ahead and find the first element. We've got the second loop that actually, does the iteration. But within that, we've got this nested third loop with its own exit test and its own increment. And this is pretty complicated, because the very first version that I showed, if we go and do the same expansion of that, that's what we get. And, these look the same to me. And they don't look the same to the compiler either. So perhaps a sufficiently smart compiler, perhaps a really clever optimizer can see through all these extra loops. And, well, yeah, maybe, but not today, unfortunately. So if we go and we look at this code, this might be a bit small for those of you at the back, sorry. If we go in and have a look in Compiler Explorer, so it's very, I had to change the example very slightly just to demonstrate the point even better, but we're summing rather than printing evens here, but it's the same thing. The first one on the left-hand side is the original code, and the second one on the right-hand side is the ranges code. And you can see that on the left-hand side, we've got all these lovely SIMD instructions. The auto-vectorizer has been able to see straight through our loop and give us lovely optimized code, whereas on the right-hand side, the generated code is nowhere near as nice. So you're going to get, most likely, much better performance with the old-fashioned loop than you are using ranges, or at least the filter view. So this is a bit sad. And what's especially sad about this is this isn't really something we can fix. This comes down to the design of ranges, or more specifically, the design of iterators, because iterators need to begin on track. That is, they need to have operator star immediately be able to give you the first value. It means that we have to have this separate first loop, and we have to have the separate inner loop as well, and this isn't really fixable. Or we can just hope and pray that one day compilers get smart enough, right? That's kind of all we have. So performance. Performance can be an issue with ranges. But that's not the only problem. Now, Klaus mentioned that Nico gave a talk here last year. Nico's given a lot of talks about ranges, and he is not a fan, I think it's fair to say. I do like ranges. I mean, I'm aware that there are problems, but I like the functionality. I like the things it can do. I don't necessarily agree with all of Nico's criticism, but there's one particular example that came from a recent paper by Nico that I really do think is very, very problematic indeed. And this is the example. Some of you might have seen it. So this is from P3725. It's in the last mailing or the one before that. It's quite recent anyway. So what are we trying to do here? Well, we've got a vector of strings containing just the names of some cities: Amsterdam, Berlin, Cologne, LA. And then we're setting up this pipeline. So we're creating a filter over this vector. So we're keeping the strings whose size is greater than 5. Okay, more than 5 characters. So that's Amsterdam, Berlin, Cologne. Then we're going to reverse. Okay, so now we've got Cologne, Berlin, Amsterdam. Then we're using this adapter as our value. Now this does the equivalent of standard move for each of the elements. That is, cast them to an R value. Okay, and then we're using standard ranges too. So we're going to move these 3 strings into a new vector and save that vector under the name sub. Okay, so that's what the pipeline's doing. I think if you've used ranges, or probably even if you haven't really used ranges, maybe the only weird one is as R value, but the other one I think is fairly straightforward what we're trying to achieve. Yeah? Yeah, maybe. Hopefully. So the expected result here is that sub contains Cologne, Berlin, Amsterdam. Now, I've already given you a clue by saying expected result that maybe this is not what actually happens. Can anybody guess what does actually happen when you run this code?
It crashes.
It crashes. If you're very lucky, it crashes.
It's undefined behavior because the us R value modifies the underlying object, and then the next iterator will be not valid anymore.
Yes, you are correct. So there is undefined behavior going on here. So first of all, what's the actual result that we get? The actual result that we get is that iteration just overruns the bounds of the vector and will start just reading random data from the heap. So yes, hopefully at some point you'll crash if you try and do that. But this is, in my opinion, this is really, really bad, because we're not doing anything on the face of it, doing anything wrong here as users, right? We're just composing some standard library objects, some standard library provided facilities. Yes, we've got a user-defined lambda, but it's really simple. It's something, in my opinion, that we would expect to work, right? But it doesn't work, and it doesn't work in the worst possible way. And the reason that it doesn't work, the gentleman at the front mentioned it, is because we're invoking undefined behavior. But you have to know quite a lot about ranges, in my opinion, to know precisely why this is problematic. And I know that for sure because the ranges study group mailing list, it took people quite a while to work out exactly why this is problematic. Okay, basically it comes down to the fact that the filter view says that you're not allowed to modify objects in such a way that it changes the result of the filter predicate while you're iterating. However, you can usually get away with that if you only do a single pass over the data, which it appears that we're doing here, but because of the way that reverse iteration works, because of the design of iterators, this ends up doing 2 passes, and it observes different results for the predicates, and that results in, yes, overrunning the bounds. I don't think that this is kind of, I don't think this is acceptable, frankly. I think this is really bad. I was most disturbed when I saw this example. And I think this is kind of sufficient motivation for me to think, well, perhaps we should be doing something different. So let's start to think about an alternative to standard ranges. I want a library for sequence-orientated programming that offers good performance, is competitive with handwritten loops, right? I should, generate code that is at least as good as a simple for loop. Yes, you can always like hand optimize things more, but if just a basic kind of 2-line for loop, I should be as good as that. I want something that offers good safety by default, right? Doesn't go reading off the end of bounds, doesn't like as with iterators, being prone to dangling, being prone to invalidation. I don't want those things. I want the library to be easy to use. I want it to be predictable. I don't want unpleasant surprises like the one we've just seen. And of course, if we want people to actually use this thing, we want it to be as compatible as possible with existing STL containers, existing STL algorithms. Right? There are millions and millions of lines of code out there already using STL containers, etc. We can't just pretend they don't exist. So I mentioned already that a couple of years ago, or Klaus mentioned as well, I was here, I mean not physically here, but virtually here, and I was talking about a library that I worked on that was called Flux that kind of aimed to do these things. This is version 1 of Flux. And it was my first attempt at writing a library to meet these goals. And Flux version 1, it was based around the idea of these bounds-checked cursors as an alternative to iterators. So a cursor is like an abstraction around an array index, right? In the same way that an iterator is a generalization abstraction of an array pointer. So that was kind of the big idea behind Flux version 1. And because it was quite easy to do, I added this optimization using what was called internal iteration, right? So for certain combinations of algorithms and adapters and sources, you could get on this fast path and use a different iteration scheme, and your code would go really, really fast. And I did my best to kind of offer good compatibility with the STL. So if you had this Flux sequence, if you built up a pipeline, it was automatically a C++20 range. And if you had a contiguous range, that is, you had like a vector or a string view or a span or something like that, you could automatically use that with Flux version 1 as well. The problem was, or one of the problems with version 1 was that if you had something that was not a contiguous range, something that was only bidirectional forward, Flux didn't really offer you very much, right? You could use it, but it offered no performance or safety benefits over just using ranges. Pretty much all we could do was wrap your iterator up and pretend it was a cursor, even though it wasn't. Okay, we're going to just take an aside for a second, because I mentioned this thing, internal iteration. So who knows what I mean when I say internal iteration? Is that we got one hand? Okay, come on down. No. Okay, external and internal iteration. So the kind of iteration we are probably used to, because just about every programming language I think perhaps except Ruby, but almost every programming language uses an external iteration scheme, including C++. So what is external iteration? Well, in this model, we have some sort of object that holds our iteration state. We usually call it an iterator, or sometimes an enumerator. And we say to this iterator, please, can I have the next value? We pull values out of the sequence, and then we do something with them, right? And depending on the language, depending on the library, this function might have different names. It might be called next, it might be called operator ++, it might be called get next or something like that. But the point is, we are in control of grabbing the values, right? We say, that is, we, the end user, the author of the algorithm, say, please, can I have the next value, right? We are externally driving the iteration. Internal iteration is a bit different. Internal iteration works more like having a customizable for each algorithm, okay? So if you imagine we had a function like for each on a vector, and you would pass it a lambda, or pass it a function and say, please, will you call this function for each of your elements? I don't care how you iterate through it internally, you can do whatever you like, just call my function. Just call this function for each element, please. Okay? And what this means is that the collection, the sequence itself, is in charge of driving the iteration, right? The iteration happens internally to the sequence. Okay, internal versus external iteration, there are pros and cons. A very, very broad generalization is that external iteration is more flexible, is more powerful, you can do more with it. Okay, and that is why almost every programming language uses it as the default model. In particular, the most useful thing really is that you can iterate over multiple collections at the same time, right? You can say, I want one value from here, and then I want one value from here, and then I want another one from over there, and I want two values from here, and you can do that very easily. Whereas internal iteration, you can't really do that because you don't have any control over it, over when iteration stops, breaks, right? You're just saying, like, please execute for this function for all of your values, and you can't. You can interrupt it sometimes, depending on the design of the library, but you can't, in general, restart it after that. However, internal iteration very often is much easier for the compiler to see through, much easier to optimize. We get really, really great performance with internal iteration schemes. We're going to see an example of that very shortly. So if you want to know more about this, I guess we can put the slides up afterwards, but there's this great blog post from Bob Nystrom, who's might be a well-known name to some of you. So he wrote this back in 2013, but there's two parts to it. This is a link to part one. This is my opinion anyway, so the best introduction to finding out the difference between internal and external iteration and the pros and cons of that. All right, that was an aside, internal iteration. Now you're all experts, right? So let's go back, Flux V1. What did I learn from doing this? Well, I mentioned we have this internal iteration fast path, right? And this offered really, really, really good performance. In fact, this was pretty much everybody's number one favorite thing about Flux. Right, because I originally started the library because I was bothered about safety problems in ranges. That's kind of where I started. And then I put this internal iteration thing in just because I could, just because it wasn't very difficult to do. And then when people would talk to me about Flux later at conferences and stuff, they'd be like, oh yeah, like I used it and it was really fast. And I'm like, and it's safe as well. And they're like, oh, is it? Oh. Anyway, internal iteration is great when you can use it. However, it couldn't be used for algorithms which needed to pause and resume iteration, right? The way it was designed in Flux v1, really, really good for beginning at the beginning of a sequence and iterating through up to a certain point, but you couldn't just pick a couple of values, stop, go and pick a couple of values from over here. You couldn't do that. It was also quite easy to accidentally fall off the fast path. Because this was an optimization, if you just changed a couple of little things, you would fall back to the non-internal iteration, which was very often slower. Cursors are a really, really great interface for multi-pass sequences. That is, for where we want to visit elements more than once. Okay? And there are many algorithms that you want or need to be able to do that, but not all of them. Cursors are a great interface for that, but if you try and generalize this backwards to single-pass sequences, then as with iterators, this becomes really problematic. And it was problematic in Flux v1 for the same reason that I said that iterators were problematic when we saw the filter example, because Flux had the same thing where we wanted to start on track. And this leads to the to the filter view in particular having this kind of bad code gen. Now, Flux, we kind of avoided it because you could very often go on the internal iteration and it wasn't that bad, but like it just wasn't a great design. The lack of support for node-based containers, I mentioned this. This was a major barrier to adoption. Again, a lot of people would come up to me and say, you know, I watch your talk, it looks really good, but you know, if I can't make my hash table work with Flux, then you know, I'm not going to be able to use it. So that was a major barrier to adoption. One thing I did find though, when I tried changing it, is that people really like composing their pipelines with dots instead of the pipe character. Right? People really dislike the overloading the it's a bitwise OR, isn't it? The pipe character. Just being able to use the dot key, people really like that. So yes, that's good at least. All right, so with these lessons learned, let's think about what to do for the next version of Flux, Flux v2. I spent a very long time thinking about how to solve these problems. Many different prototypes, many experiments, many failures. But I came up with something that I think is really good and works really well. Okay? And that's what I'm going to spend the rest of this talk telling you about. So here's the big idea. Instead of having an interface that's one interface that's really good for multi-pass sequences but doesn't work very well for single-pass sequences, and instead of having an optimization that works really well but is kind of unreliable because you might fall off it at any time, how about we provide distinct interfaces for single and multi-pass sequence access, and we have the single-pass model that is guaranteed to use internal iteration, uses an improved model over the original Flux v1, guaranteed, reliable, high performance, and for multi-pass sequence access, we can keep fundamentally the same model, but we simplify it slightly, make everything a little bit cleaner, and actually even safer than it was before. And that's the collection interface. Iterable and collection. So I want to start with, I'll just add in this little disclaimer. This is the current development version of Flux that I'm referring to. There is no release yet. It's real soon now, any day now, I promise. But it's the current development version. You can find it on the GitHub, on the devel branch. Naming and other details might differ between this talk and whenever I release version 2.0. But it does mean that if you do have any feedback as a result of this talk, any ideas, anything you think I haven't thought of, anything that you think would be good to change, now would be a really good time. Okay. So with that out of the way, let's dive into the new model, and in particular, the iterable protocol. So the iterable protocol revolves around something called an iteration context. And iteration contexts are the things that are responsible for actually doing the work of iterating. And to write an iteration context, you need to provide two things. Firstly, you need to tell us what the type of the element that we're iterating over is, right? Element type, this can be an object type, it can be a reference. And you need to provide a member function template run while that takes a unary predicate and returns an iteration result. So iteration result, this is just an enum that says, did we reach the end of the sequence or did we break early? Okay? A type def and one function. So we provide a predicate to this run while function, and what this run while function does is it enters a loop and it calls your predicate for each element of the sequence, and if your predicate returns false, we break out of the loop and we return this iteration result incomplete. Otherwise, if we run out of elements, well, we're finished looping and we return iteration result complete. Now here's the thing. If we return incomplete, we guarantee that the next call to run while will resume iteration from the next element. Okay? It's really important. Doesn't necessarily have to be with the same predicate. You can provide a different function, meaning you can use one function to iterate over the first 10 elements, another function to iterate over the next 10 elements, and so on and so forth. And the iteration context basically needs to maintain any state necessary to allow this to work. Okay, this, it turns out, is exactly the same state that an iterator needs to hold. So iteration contexts are reference types. They will typically hold a pointer to their parent sequence or equivalent, something that's morally equivalent to a pointer. To avoid problems with dangling references that are very common with STL iterators, contexts are typically they're non-movable and they're non-copyable. So this helps to prevent references escaping out into the wild. It also prevents problems. There can be issues where you pause iteration, you move the context, and then you resume iteration. That can be quite difficult to ensure that that works in some situations. So if we just say that contexts are non-copyable, non-movable, those problems go away. Although I'm focusing on them here because I want you to know how this stuff works behind the scenes, for end users, iteration contexts are mostly an implementation detail. Okay? We have higher level algorithms on iterables, and so it's only people who are kind of writing low-level algorithms, writing iterable adapters that actually have to, deal with contexts directly. So let's have a little example of what an iteration context looks like. Here's one that just does the equivalent of views iota, if you're familiar with that, right? We're just going to provide you with some ints. So the state that we're going to keep hold of, we're going to have the current value, and we're going to have the upper bound, so when to stop. We're going to have a constructor. We have the element type def. In this case, our element type is an int. And then we're going to have this run while function. So this run while takes a predicate, uses a supply predicate, and returns an iteration result. Run while, it encompasses the loop. It has a while loop inside it. So while current is less than bound, that is, while we haven't reached the end, if the predicate returns false, so we pass it the current value, and as kind of a side effect of that, we bump the current value as well, but we return the old value, call the predicate with the old value. If that returns false, we break out of the loop. In fact, we break out of the function. We return iteration result incomplete. Otherwise, well, we've already incremented current, so we just go back to the start of the loop. And if finally, once current is equal to bound, we're done with our iteration, and we return iteration result complete. So what you'll notice here is because of this pre-increment, if the predicate returns false, if the user says, hang on, I want to pause, then we return incomplete. But the next time, on the next call, to run while, current has already been incremented. Right? So we're ready to go again. So this is how you would write an iteration context that's basically the moral equivalent of views iota. And I don't know if you've looked at the implementation of views iota, but it is quite a lot more complicated than this. But actually, this kind of fundamental pattern, we can generalize this quite easily. And in fact, we can generalize it for any STL range, any forward range. This is fundamentally the same as the code we've just seen, except instead of a pair of ints, I'm now using an iterator and a sentinel. And this requires a forward range because we're doing iter++. It's not very hard to do this for any input range as well. It's very slightly more work. But we can write an iteration context for any input range. So now we've got an iteration context for any input range, any forward range. We can use any STL range with this model. So that's pretty great. OK, so what can we do with iteration context? Well, the first thing we can do, we've already seen it. We've got this function run while. And this does the internal iteration that we were talking about. Okay? This calls the function for each element. And this, if you use run while, you're going to get the really nice high performance. This is really easily optimized by the compiler. Okay? So we have this wrapper function. It just calls run while on the context. We also have this function, next element. And what this does is it returns an optional of the element type. How does this work? Well, we initialize an empty optional, we call run while, and we pass it our custom lambda. And what this does is it emplaces the value in the optional, and then immediately returns false to say, let's halt iteration here, and then returns that optional. So this allows single stepping through sequences, right? This allows us to switch from the push-based iteration to a pull-based model. This allows us to have the best of both worlds. We can write all the algorithms that we need to, where we pull one thing from over here and another thing from over there, another thing from over there. We can do that with this next element function. But when we're doing actually the more common thing of just beginning at the beginning of a sequence and doing something for each element, we can do that with run while, and we get the really high performance, right? So this offers us the best of both worlds, all in one neat model. But as I mentioned, iteration contexts, they're kind of the low-level, what's the right word? They're the low-level machinery of how this works, but most end users, they won't have to deal with context directly. They deal with higher-level iterables. How do we write an iterable? Well, it literally couldn't be easier. You write one function. That's it. One function called iterate, which returns an iteration context. That's what you have to do. You can also optionally provide a const qualified overload of iterate as well to provide const iteration if you wish. So let's have a look at that. We have this high-level ints object. Just hold the start and end value, and then we provide this flux iterable traits class template. And what you can do is the end user to define your iterable is you can provide a specialization of this, in this case for the ints struct. And we just provide an implementation of an iterate function that returns us the ints iteration context that we already saw. But actually, there's an even easier way to do this, because if you don't want to specialize a class template, you can just write a member function that returns a member function called iterate that returns iteration context. So that's pretty neat. And of course, most of the time, if you were doing this in sort of real life, you wouldn't have this external ints iteration context thing. You make it a nested type. So this is kind of the more realistic result. And actually, this is taken pretty much directly from the Flux source code. This is what it really looks like. In real life, it's templated on the integer type, but apart from that. So the point I'm trying to make is, if you look at the ranges code, this is just like, at least in my opinion, like an order of magnitude simpler than the kind of ranges interfaces that exist in the standard library today. So what does this look like in use? Well, for straightforward functions like a fold, often called a reduce in certain languages, in some languages, we can just use run while, and we can iterate straight through from beginning to end, roughly like so. So we initialize an iteration context, we call run while on the context, and then we do the fold operation. That is, we update the initial value with the result of this user-declared function. And then we return true from our lambda, because we never want to break, we just want to go straight to the end. And the fact that we always return true from this lambda means that in our while loop that we wrote, this had this conditional, but the compiler can see that the result of the lambda is always true. So it just removes that check completely, and we get really well-optimized code. So we can write straight through high-level functions on iterables like this. We can also write functions using iterables that take pairs. This is a thing that's traditionally very difficult to do with internal iteration, but we can do it with this model. Okay? So here we're implementing the equivalent of standard equal. So we take two iterables, we fire up we create their iteration context for the first iterable and for the second iterable. And then this time we're using step-by-step iteration. So we call next element on the first context, gives us an optional. Next element on the second context gives us an optional. If both of those optionals are engaged, if they both have values, we compare the values. If the values are different, then we know that the two sequences had different elements, so we can return false. Otherwise, if one of the optionals was engaged and the other was empty, then the sequences had different lengths, so we know that they're not the same, so we can return false again. Otherwise, neither optional was engaged, meaning we reached the end of both sequences. So in that case, we can return true. So the purpose of this to demonstrate that we can quite easily write algorithms on multiple sequences, multiple iterables at once. Okay, and actually, is anyone familiar with the Rust iterator model? Right. A couple of hands. Maybe people don't want to admit it. Because this is actually very similar. This next element is very similar to how the Rust iterator model works, if you're familiar with that. So this is pretty much the same. I mean, obviously, different names, but it's the same algorithm shape as how you would write this with the Rust iterator model, which is pretty neat. So that's algorithms, things like fold, things like equal, all of these things that are in the STL kind of ranges namespace, all of these terminal algorithms. We can write those using iterables. But we can also write iterable adapters. These are things like standard views filter, standard views transform, etc. Of course, we can write iterables that adapt other iterables. We can build up pipelines. And as ever, as with ranges, as with all of these libraries, this requires a little bit more work than terminal algorithms, but less so than the original version of Flux, and much, much less so than C++20 ranges. Okay, so the way that it works is that an adapter will provide its own iteration context that wraps up the iteration context of the underlying iterable. And the adapted context's run while will call the run while on the base iterable. Okay, that's generally how almost all of these adapters work. So we're going to have a little look at what the filter adapter looks like. And again, this is not me simplifying things for slide code. This is kind of how it actually looks in the library. And if you're really curious, I suggest you go and have a look at the ranges, how that looks, the filter view in the standard library if you want to compare how things look. Okay, so we have this filter adapter. We're going to take some base iterable, and we're going to have our filter function, our filter predicate. Okay, we need to store those in the filter adapter. Then we're going to have our adapted iteration context. So this is templated on the base context, that is the iteration context of the base iterable. So we need to store that. We also store a copy of the filter function because that's useful for locality. The two things we needed from an iteration context. We needed to know the element type. Well, in this case, it's the same as the base context's element type. And now we need to call run while. We need to implement run while, rather. And what we do is we call run while on the base context, and we pass it a lambda that actually does the filtering. Okay? So we invoke the filter function on the element that we got from the base context. If it passes the filter, we then go and call the user's predicate. Otherwise, we return true. That is, we say we want to continue iteration on the base context. So we wrap up the base iterables context, and after that, all we need to do is we need to provide just our two-member functions, iterate, which returns a context type initialized with the base context, with the base's iteration context, and also a const overload if the base iterable is itself const callable. So now let's have a bit of a throwback to the beginning of the talk and see what this actually looks like in use. Because we're going to go back to looking at this function. So this was the print evens function, and this was the nice simple version, and then I adapted it to use ranges, views filter, and it didn't look very good. So what happens, and that was v2, so what happens with v3? So what happens if I now use this new Flux filter with this new lovely iterable model? And I'll write it. There are various ways you could write it. This is one way you could do it. Well, we're going to play the same game. We're going to pretend we're the compiler. We're going to inline stuff, and we're going to see what this expands out to. Okay? So the for each call, what we do is we create we call flux iterate on our iterable. This gives us a filter iteration context. And then we call run while on this iteration context. And for each just returns true from the predicate. That is, it just loops all the way through. Okay, well, we've just seen what the filter iteration context does. It wraps up the base iteration context. Okay, so let's expand that one out. Well, our base element here is the vector. Okay, and again, we saw how the new iteration model iterates over a vector or any kind of range. It uses this range iteration context that we've already seen. So we can further expand it like this. And now we're calling run while on the range iteration context with this slightly more complicated kind of nested lambda. Slightly more complicated to us, but not really to the compiler, because it's got this immediately invoked lambda, and it can see just straight through this, right? It could just inline this straight away. It says, okay, so from the first branch, I'm going to just, if the predicate, the even predicate returns true, I'm going to print and then return true. Otherwise, I'm just going to return true. And this is pretty simple for it to transform into code that just looks like this. Right? This is the moral equivalent of what it was doing before. Okay, so we've already seen what run while looks like on a range iteration context. So we can go through and we can substitute all that in as well. Okay, so we hold on to an iterator to the start of the range, an iterator to the end of a range, and we substitute in this while loop. This is what run while on the range iteration context does. And I've set it up. You know, again, looks a bit complicated here, but not to the compiler. Because the compiler can see that this lambda, this predicate here, always returns true, so it doesn't actually need the branch at all. It can simplify it to this. And this looks very, very much like what we started with. Again, this is the expanded version, just for comparison. And you can see that other than the fact we're incrementing the iterator in a slightly different place, this is basically identical. And just to prove it, this is the Godbolt comparison using this new iteration scheme. And you can see that we get the same lovely vectorized SIMD code generated for this new iteration scheme that is just as nice as the handwritten loop. You should be thanking Trang, not me, but you know, it's very pleasing. There's something else that's actually, you know, I think this model is all about simplicity. I know that all the inlining kind of got a bit complicated, but we could see through it and the compiler could see through it. And, you know, I've tried to make it as simple as possible and yet quite powerful. But there's actually something that kind of falls out of it as well that is just so much simpler than the way ranges does things, and that's reverse iteration. Because, again, in the way that reverse iterators or reverse iteration works in Flux today is pretty much the same as it works in the STL. But with the new iteration model, actually things get dramatically simpler. Because we have this reverse iterable concept, And you can make an iterable into a reverse iterable just by providing a reverse iterate function that returns an iteration context, right? And it just so happens that this iteration context goes through the elements backwards. So we can write, for example, an iteration context that takes a bidirectional range, and when we call run while, it just returns the elements of this range in reverse order. So again, this is an iteration context. We need to provide two things. We need to provide the element type def. In this case, it's the reference type of the range. And we need to provide an implementation of run while. Okay, so what do we do in here? Well, whilst our iterator is not equal to the start, because remember we're going backwards this time, now, slightly different. We pre-decrement our iterator and then pass that to the predicate. And if that returns false, then we return incomplete. Otherwise, we head back to the top of the loop. And once we run out of elements, once iter is equal to the start, we can return iteration result complete. Now, what's really, really neat about this is if you know about the way that standard reverse iterator works, operator star on a reverse iterator has to do something a bit weird, right? Klaus is smiling at me because I think you know this, right? Yes. Because it needs to do an extra decrement, right? Because if you think about the way that reverse iterators work, we start off, let's do it this way. We've got our first element, 1, 2, 3, 4, and then we've got our past the end sentinel value, right? And then when we create our reverse iterator, we start off with it pointing to this end value. But then, again, this is because we have to start on track. When we call operator star, well, there is no value here. So what we've got to do is create a temporarily decrement our iterator, look at this one, and return the value of this guy here. So this extra pointer decrement happens every time we call operator star on a reverse iterator. And it's something that gets in the way of optimization, right? It's not terminal. Actually, reverse iterators, they usually optimize pretty well, but it's something that can get in the way. And with this doesn't happen. There is only one decrement happening here, right? We don't have this extra step. Right? So this is more amenable to optimization. So this was our filter adapter as we saw it before. This is we had this templated filtering iteration context type. What we're going to do now, and hold on to your hats because this is going to get a bit complicated, we're going to make our filter adapter handle reverse iteration, okay? So just bear with me on this one. So, okay, we have what we had before. We have our iterate function, so this is for forward iteration, returns the context, our filtering context, based on the the basis iterable iteration context, and again for const iteration, this is what we have to change to handle reverse iteration. We just add a function called reverse iterate, and that's it. This is literally all we have to do. We do it once for mutable iteration or non-const iteration, another time for const iteration if the underlying type supports it. And that's literally the only change we have to make, right? This is just, I think this is kind of wonderfully simple, that it just kind of falls out of the model, right? I didn't have to do anything special to support this. It just happens. And of course, yes, we can provide a reversing adapter that, again, is just wonderfully simple. All it does is that if you call iterate on the reverse adapter, it gives you the reverse iteration context. And if you call reverse iterate, it returns you the forward iteration context. And I think that's just really nice. I just wanted to show it off because I was pleased with it. Okay. I'm not going to take up all that much more of your time because the iteration context, this new iterable model, I think is really lovely, really kind of elegant actually, gives us the best of both worlds, gives us this really highly optimized code when we're doing simple things, but also allows us to do more complicated things like, stop-start iteration when we need to do it. I briefly also want to talk about collections. This was the other element access API, right? This is for multi-pass iteration. This is when we want to provide effectively generic access to elements of some collection. So it's the equivalent of forward ranges, if you are familiar with that. So this is largely the same model that version 1 of Flux used, but slightly simplified and made slightly safer as well. So the iterable concept, as I said, is all about single pass iteration. The collection concept is about multi-pass iteration. All collections are automatically iterable. Okay, the collection concept subsumes the iterable concepts. Right, we provide a default implementation of iterate if you write a type that is a collection. So you don't even have to do that yourself. So the collection API revolves around these things called positions. These were previously called cursors in the old version of Flux. Now we can call them what they actually are, right? Which is positions. Every collection has an associated position type. And a position is a generalization of an array index. In fact, if you are using a contiguous collection, something like a vector or a string view or a span, the position type literally is an integer, right? It doesn't have to be, but it's, that's the best way to think of it. It's a generalization of an array index. This is in contrast to iterators, which, as I mentioned earlier, they're like a generalization of array pointers. The key thing is that, unlike iterators, position objects are not smart. So iterators, you can advance an iterator, and they know how to advance themselves, they know how to dereference themselves. They are reference types, they are tied to their original range, and this means that that iterators are really prone to being invalidated, to leaking, to dangling. Positions objects are not smart. Position objects, you think of them, they're basically just like an int. And if you're holding on to an integer index and your vector goes out of scope, what are you doing? You're just holding on to an int. There's nothing dangerous you can do with that, right? You can't dereference the int and get a dangling, the reference to some deleted memory or anything like that, as you could with an iterator. So the only thing that positions do is they denote an offset from the start of the collection. Right? So position objects must be regular types, that is default constructible, copyable, equality comparable, and additionally, they must have a strict total order. That is, we can compare them with the usual comparison operations, less than, greater than, etc. And when we compare to two positions, if P1 is equal to P2, then they represent the same position in the sequence. If P1 is less than P2, then P1 occurs earlier in the sequence. It's pretty straightforward, I think. And the key point is that by insisting that our position objects are totally ordered, which is a new requirement compared to the old Flux model, by the way. But by adding this requirement for a strict total ordering, we can perform cheap, uniform bounds checking for all collections. automatically. And in particular, we can perform bounds checking for arbitrary slices of collections, which again is something that was quite difficult to do with the original Flux model. So what do we have to do to define a type as a collection? We need to provide 4 functions. First of all, begin pos. This is like begin for iterators, but it returns your position, right? End pos, again, like end returns you an iterator, but this returns you the end position. We provide a function called inc pos. That is, we increment the position. Takes the position by reference and increments it in place, so it now points to the next element. And finally, if you're an end user implementing the connection API, there's one more function you have to provide, which is called read at unchecked. And what this does is it reads at the position, returns the element at that position, but the unchecked part means that you are allowed to assume that someone else has done the bounds checking for you, right, as the implementer. And the reason we do that is because it allows us to implement a try read at function without doing double bounds checking. Right? There are other circumstances where you want to get that last 1% of performance. Maybe you don't want to have a bounds checked read function, so we make the basic implementer provided read function. We allow them to assume that someone else has done the bounds checking, and because of the way positions are designed, we know that we can always do the bounds checking ourselves cheaply and uniformly. So what does this look like in practice? Well, here's my array type. It's the equivalent to standard array, just holds, wraps a raw array of n t's. So we implement begin pos. In this case, our position type is just a size t, and we begin at index 0. Our end pos is the size of the array. We can increment our position by just, well, incrementing the position. And finally, our read at operation, read at unchecked, we just return the position element of the data array. And we do that for const and non-const access. We could sort of do this in one function if we were clever, but it's easier if we just do it twice in this case. So we say that the position is valid if it's greater than or equal to the begin position and less than or equal to the end position, right? So a valid position is from, in this case, 0 up to and including n. And a position is readable if it's up to but not including n, right? So valid positions and readable positions. We provide these functions, is valid pos, is readable pos, that give you the answers to these questions. Because sometimes you need to know, sometimes you want to return the sentinel position, but no further, and you want to bounds check that. So then you'd use is valid pos. Sometimes you need to make sure that the position you're returning is readable, so you'd use the is readable pos. So kind of 2 levels of bounds checking, depending on whether we want to include the end position or not. So we have this wrapper function read at. This calls is readable pos, and then if that passes, calls the read at unchecked function. And I already mentioned we have try read at that returns an optional rather than trapping. So read at, if the bounds check fails, we crash a program, basically, which is safe but kind of not very friendly. So we have this try read at function that returns an optional instead if you want to handle failed bounds checks. So as with ranges, we have a bunch of high-level refinements of the collection protocol as well. So we have permutable collection. This is a collection where we can swap elements. This is, again, very useful for doing in-place algorithms, things like rotates and sorts and things like that. We actually provide a default implementation of this swap at function if your element type is a mutable L-value reference. We can have bidirectional collection, which allows us to decrement positions, so pretty much the same as a bidirectional range. And of course, all bidirectional collections are automatically reverse iterable as well. And we have random access collections that offer two additional functions as well. We have a distance function that returns the distance between two positions, how many elements there are in between. This could be negative if pos 1 here is later in the sequence than pos 2. And we have the ability, of course, to do a random access jump. That is, we can jump n positions, do n steps in one operation in constant time. And contiguous collection offers unsafe access to the underlying storage. So this is like .data on a vector or a string or something like that. It allows us to do low-level operations like memcopy and stuff like that when we have contiguous elements. So that's pretty nice as well. So just finally, I mentioned this before, that I think this is the absolute bee's knees. I'm very pleased with it. But if I can't make it compatible or at least interoperable with existing STL code, it's never going to get anywhere. So, and this was kind of something that didn't go so well in version 1 of Flux. So aiming to fix that, now every single C++20 input range is automatically iterable. That is, you can use all of the iterable APIs, all of the algorithms that operate on iterables will work for any C++20 input range. And additionally, every bidirectional range is automatically reverse iterable. In fact, we've already seen exactly how that's implemented. Going the other way, if you have a Flux iterable and you want to use it with some ranges algorithm, you can do that. You need to use this adapter function called asRange. So you would have your Flux sequence, you say .asRange, it's going to return you like a view, and then you can pass that to your, you can call .begin and .end on it and do whatever else you need to do. Actually, for range for loops in particular, we have this little trick where you can use a range for loop without having to do this asRange. So that's actually quite neat as well. Every collection is automatically a C++20 forward range. That is, for collections, you don't need this asRange thing. You can just call begin and end on any collection, and that will work. And every sized random access range is automatically a collection as well. The reason is because we can we can easily bounds check sized random access ranges, so we can provide the safety guarantees of the collection API. So, today's version of Flux offers, and I'm pretty sure, I'm quite confident that the performance that we get from Flux is the best in class of any general purpose iteration library. So there are things like Thrust obviously is going to get better performance because it's GPUs, but if you're just talking about something like C++20 ranges or something like Rust iterators or something like enumerables in C# or things like that, you're going to get really good performance with Flux when you're on the internal iteration fast path. And with Flux v2, we can guarantee that in more situations because we have this protocol that is completely designed around it. Iteration contexts, they know their own bounds, they don't overstep them, right? Unlike with iterators where it is really easy to overstep the bounds. The collection protocol for more complicated situations offers safe, bounds-checked, generic element access. The equivalent, everything you can do with a forward range, you can do with a collection, but you can do it in a way that is safely bounds-checked. Hopefully, I've managed to convince you that this is faster, safer, better alternative to ranges. I hope I've managed to interest you in it. If you are, you want to go and have a look at this, that's the URL for the Flux library. As I said, this is currently the development version. You can have a look at the devel branch. There's also, if you go to the discussions tab, there's a really long post that I wrote that sort of goes into a lot of detail about how this works, even more detail than I've mentioned today. So if you've got a spare hour or so, you can spend your time reading that. But otherwise, that's it from me. So thank you very much for listening. We have, oh.
Question, is your library already started to support const expressions and const evals?
So everything is const callable, everything that can be. Yeah, so we have an iStream wrapper that is obviously not, but everything else, the entire library is const extra. And all of our testing actually is done at const extra time. Because it's really, I don't know if people know this, but you can't have undefined behavior at compile time, right? So if you run your tests as part of the compilation process, if you have any undefined behavior, the compilation will stop and you will get an error message. So by running all our tests at compile time, we can check to make sure we're not accidentally invoking UB. It's a really powerful technique.
Thank you for your presentation.
I'm not. Oh, hi, sorry.
Just in the title you say faster. Do you have any numbers for that?
I don't. There is a presentation by Connor Hoekstra that he gave at C++ Under the Sea last year, where he tests a whole load of these libraries against one another. And he basically found that Flux was the fastest, which at least until the problem size got big enough that it was worth putting on a GPU. Then obviously, like CUDA, Thrust, won out. But for reasonably everyday problem sizes, the Flux model was fastest. So I was quite pleased when I saw that.
How much?
How much? Well, I mean, it varies. So. I like to say that it's never slower than ranges, right? But it's quite often a lot faster because we can, the compiler can more easily see through things, so you can get this auto-vectorization that we saw on the Godbolt examples. Now, if you do a really artificial benchmark against something that's auto-vectorized and something that's not, maybe you're going to see a 10 times speed difference in that micro benchmark. But that's not realistic. So I don't want to go out and say, I could very easily just do an artificial benchmark of that some example that I showed and say, you get 8 or 10 times speed up. But that's not really what you're going to see in your real application, all across the board. But I believe that it is the fastest library of its kind, and we generate the best code. At least I hope. That's the intention.
Yeah. Thank you very much. So you convinced me it's faster, better, and also safer. What I'm not so convinced about, and maybe maybe just my feeling, this is called collections. So you have something like RAMs, so like random access memory, but why call it collection? So that's not so clear about.
So
Against my intuition, maybe it's wrong. I'm not an expert in C++, but in collections I associate also something like a set without an index.
yes. So naming is hard, right?
Why not call them RAMs? It's shorter. If you're
RAMs, RAMs, but not every collection is random access. Right? You can have a collection that is.
Your collections have always an index, so you can always random access them.
No, that's not the case. You can so you can. How to give you an example?
You can go 2 slides back. That was written. It's like always random access.
So okay, every sized random access range is automatically a collection, right? But you can write collections that are not random access. It's just you don't get it automatically. But you can, if you want to, you can. I showed you the implementation with the 4 functions, begin pos, end pos. You can write a collection implementation that is not random access. And in fact, even if you start off with a random access range, you might pass it through a chain of adapters and end up with something that is not random access.
Maybe
Right.
call it indexed or something.
Index. Yeah. So I see where you're coming from. Actually, I got the name collection from Swift. So Swift has pretty much the same idea, and it calls it collection. So originally, this was a multi-pass sequence, is what I called it.
I don't have to say they are also wrong.
So you showed how to implement the position for an array type.
Yeah.
Could you quickly explain how that would look like for like a list, like a link-based type, so you can't just use the integer?
So a linked list, how would you go and implement it for a linked list? You can't. That's the very short version, because what the collection API wants is to be able to bounds check positions. And for a linked list, what do you have? You have a node, you have a pointer to the start node, and that has a pointer to the next one, and that has a pointer to the next one. And the equivalent of bounds checking would be to ensure that the object that you're pointing to is still live, right? And that's just not something we can really do in C++, unless you can do it if you if you control the original allocation and you just instead of holding node pointers, you hold indices to this original allocation. You can do that. You can implement the collection API that way. There are a couple of alternatives. You can also do things like generation IDs. So every time you modify the container, you bump the generation ID, and then you can check that the container hasn't been modified since you created the position object. That's another way that you can do it. But for a generic, like a basic linked list, like standard list, you can't implement the collection API. But you can implement the iterable API, right, which is kind of the point. So that was what was tricky about version 1 of Flux, was because you couldn't implement what I was then called sequence, and so you were stuck. You couldn't basically use Flux at all. Whereas now, you have all this iterable goodness, and you're going to get, well, you're probably not going to get great performance because you're using standard list, but at least it works.
Hi. So I was impressed by the first example of undefined behavior, and I thought I was waiting until the end to see how you would resolve the similar problem with your framework so that we can compare apples to apples. Right? So this is definitely missing. When you call it faster, currently we live in an era that you have Spark, you have Extensa, you have R that gaining momentum, but you tested it only on x86, right? When we talk about all of these libraries, we need to make sure probably more the world to see how this will get loaded. And to be honest, when I would go for ROI to my management with ranges, they will ask why we should invest right now. would it be possible in the future to have these ranges executed on GPU, or whether we can offload this? Because this is where it's all coming, right? Filtering will be more comfortable with probably GPU for the big data. What would you recommend me to tell to my boss for ROI of using ranges?
Wow. Well, obviously, I think Flux is great, and you should tell your boss that. No, it's like you make a good point about GPUs and multi-core and all of that sort of thing. We have this standard execution coming in C++ 26. This is this executors, as it's called, this sender-receiver model that promises to allow us to write algorithms for a huge class of asynchronous devices and modes. That's where the future is going to be, right? And one day, once it's available, I really want to make Flux work really well with the executors model, because that is absolutely where the future of it lies in C++. We're not there yet. We're not there. Flux is not there. The standard library is not there in providing you the algorithms. Being able to do things like filter on a GPU is not there, is just not there yet. But we know what the future is going to be. We just have to kind of marry the two together: the low-level executors API and the high-level things on ranges.
Will you add the slide for apples to apples comparison?
Apples. So the apples to apples. Do you mean the ones with the cities?
The ones with the cities.
Okay. Well, I can tell you what happens. It works. Okay. So I'll go into more detail. With Flux today, if you convert that exact example, what happens in Flux today is it crashes. We fail a bounds check, right? That's a lot better than reading arbitrary memory, I would say, because we guarantee to crash a program rather than reading arbitrary memory. That's version 1 of Flux. With Flux v2, it works. And it's a very good idea. Next time I give this talk, just after I mention reverse iteration, I will call back to that example, because yes, with the new Flux model, that example does in fact give you the exact expected result. It just works.
Other questions?
You say crashes or works?
Sorry, Flux v1 crashes. Flux v2, the new model, what I've presented today, the new one works. Gives you the right answer.
Other questions?
I had a question about the posing that you did, slide 44 kind of. You had the flux ref, dot filter, dot stuff.
Yes.
What is implementing filter? So the question being, like, let's say I want to add another adapter like Stride. Do I need to go and add its composition with filter, with other stuff?
Yeah. So which slide number did you say it was?
44.
44.
That was wrong. It's not 44.
Yeah, something.
A couple of slides before this.
I think I know where it was. Let's get through all this.
Yes.
Here, yeah. So .filter.sum. Yes. So this is what I was saying, that in Flux we use the dot for chaining. So how does this work? How do I put this nicely? It's a bit of a hack.
Return something on which you can call the object.
Exactly. So this Flux ref is like standard ref, like reference wrapper. It returns you a reference wrapper, and that object has a whole bunch of member functions called things like filter and sum. So Flux ref returns you this reference wrapper object, a Flux reference wrapper that has a filter member function. When you call .filter, it returns you a flux filter adapter object, and that has a lot of member functions, and one of those member functions is called sum, so you can build up these chains. The way that that works is it's really quite messy, and I really wanted to move away from it because it causes quite kind of implementation difficulties. You have to make sure headers are always included in the same order and things like that. Causing me headaches in terms of implementation. So I wanted to kind of, all right, well, we'll just start using pipes like the standard library did. And I proposed doing this, and everybody yelled at me that they really like these dots and they absolutely don't want the pipes. So I'm going to have to make this work. But your question was, how would you write your own custom adapter?
Yes.
Yes.
I lost the mic, but if I understand correctly, if I wanted to add like dot stride, I have to add all the existing adapters. I've got to add support for them to my adapter and update every other adapter to support mine.
No. So the way you would do it if you were writing a custom adapter is you inherit from, I can't remember exactly, it's called something adapter base. And this is a templated base class, CRTP base class that provides all of these member functions as a like a mix-in, effectively. So we implement it all for you, which if you're doing your own, it actually works really well. Inside the library, it is a bit more awkward because we're trying to implement return the filter adapter from a function that has the filter function. It just all gets quite circular, right? For third-party adapters, you can't just say like dot stride. What you do is you say dot underscore open brackets and then your stride adapter, whatever your adapter name is called, then whatever arguments. So we've got this wrapper function that's just called dot underscore, and that's how you expand this for third party, like your own. You don't need to write stride, by the way. We've got a stride adapter, but if you wanted to write your own, that's how you would do it, right? So you can't just say like dot my stride or something. You would have to say dot underscore open brackets my stride, comma, whatever arguments your stride type took, and we would integrate that as part of the pipeline.
The dot underscore bracket is effectively fine.
Yes, yes.
You said for node-based collections like list, like the list of or map, this won't work, right? You can link list, it won't work, right?
So to be clear, the iterable API, it works.
On the list, it provides iterator, right, on STL.
Yes, so you've got a list provides STL iterators. STL iterators have the associated problems, dangling, unsafety, bad performance, all of that stuff, right? We want to do something better than STL iterators. And so you can use all of the iterable functions you can do with standard list. What you can't do is implement the Flux collection API for a standard list. And the reason is because there is no way of being able to provide guaranteed bounds checking for a standard list. If I say, okay, position the element at position 42, the only way I can do that is by holding a pointer to that element. And then if you go and change the underlying list in some way, my pointer is dangling, or potentially dangling. And there is no way, at least simply, without changing the implementation standard list, there's no way that I can know that my pointer is now dangling, right? So there's no way that I can offer the safety guarantees that I want the collection API to have over a node-based container like standard list.
That's exactly the consequence of calling it the wrong way. If you call it index, then nobody would guess, oh, I can use a list.
So you're saying the collection name implies that I would be able to use standard list.
We have exactly this discussion
That's,
because we call it collection.
that is, yes. That's a good argument. Yeah.
And mapping
Sorry?
Map is also a collection.
Standard map is also a collection, yes.
Unordered
Yes.
map,
Yeah.
unordered map.
You said that it's for multipass, so just call it.
It was called
fifth element multipass.
multipass sequence is what it is. Was the previous name for this? I just thought that's two really long words for people to type.
It would be nice as
Yeah. Okay. Just call it a multipass. Okay. Yes. Okay.
Yeah, I think for the presentation. So far we have push-based iteration, which is fast but inflexible, and we have pull-based iteration, which is flexible but slow. What about
Not necessarily slow, but not necessarily. But you know.
it's more difficult to optimize.
Yes.
And if you cannot vectorize it, it will probably be slow. Right?
Yeah.
Assuming you have a lot of data.
Yeah.
Have you heard about batch pulls, which is like a middle ground in between the two?
So this is where you sort of you grab a chunk of data and you do like internal iteration over that.
It's pulls, but instead of getting one element, you get like 50,
Yeah.
which you can vectorize.
Yes.
Do you think that's a good idea?
I think it's pretty neat, and I think it's also something that you could do with this model, because we can pause. So you could
You would both for something, right?
yes, you could grab a whole bunch of elements. You could save them into a vector. You could do internal iteration over that, and then grab another load of elements, and you could write an adapter that kind of, you know, grabs whatever 50 elements or 1,000 elements or whatever is appropriate at a time, and does that. So yeah, that can be a neat way of kind of balancing the two models. Yeah.
Any plans to support that? Just ask.
Not until right now. And now I'm thinking, hey, that's quite a good idea.
Let's see. Thank you. All right. Other questions?
Thank you very much for the presentation. The question was quite simple. Could you give some examples of open source based or commercial projects that use the library? Or maybe you have some collaboration, because as from my understanding, this could be some real good output for the job.
This could be, sorry, I didn't catch the last part. This could be.
I mean, at the end, it should be some real example of a good output of the job for as a Flux library open.
So as far as I know, there is nobody commercially using Flux yet. If anybody is, let me know. I occasionally have a search on GitHub and I see people are sort of experimenting with it, and a whole load of people use it for like advent of code and fun things like that. But as far as I know, there are no commercial users of Flux right now. But hopefully that will change. One of the things I would quite like to do that may well change things is that this iterable model that I was talking about today, that I think is very, very powerful and fixes a lot of the problems that we have with standard ranges. I would like to write a standard proposal that proposes the iterable model for the standard library, because I think that would have a good chance of maybe not definitely getting in, but kind of focusing people's minds on can we do things better than we have in the standard library at the moment. So with a standard library proposal, you get a lot of scrutiny, and I think that would be a good way of kind of getting people interested and, as I say, focused on the way we can do things better with libraries like Flux.
That's what I was hoping for, that you will say this.
So we are waiting for 32, right?
Sorry?
As a part of C++, 32, for instance.
Yeah, well, 29 maybe.
Okay, but this is a nice pitch for my question. You criticize the standard libraries, other people openly criticize
So since you also do some teaching, etc., would you officially recommend not to use standard ranges?
I would say that using standard ranges is better than not using standard ranges. Okay? I think that the sequence-based programming, collection-oriented programming, whatever you want to call it, this building up of pipelines, this, if you're not familiar with it, if it's not something that you've been used to or that you've kind of used in other languages, it's really strange to begin with, right? You kind of have to tune your brain into how to think about applying these filters to sequences. But once you do that, this sort of functional style that people call it, once you do that, you start seeing these patterns recurring everywhere, right? And for the most part, building up these pipelines, using these high-level algorithms, you avoid having to deal, most of the time, having to deal with raw iterators and yourself making mistakes like having dangling iterators, off by one errors, things like that, because you're just composing these high-level operations. That's really the goal of this programming model. And ranges enables that programming model, and if you are very careful with it, you can get good results, right? So I think your code will be better if you use ranges, but I think we can do even better than ranges gives you.
So you would agree that this is a technical discussion about how to do better, but it's not the mindset. Use algorithms, use ranges, simplify your code, and avoid the most common programming problems.
Yes, yes.
Thank you.
Andreas is going to disagree with me now.
I'm not going to disagree, but I have a question from one of our viewers online who is wondering about, they're asking about using this library to do safe concurrent write access in a multi-threaded program. Is that something that you have thought about? Is that something that you think could be done?
So I mentioned actually the collection protocol. One of the reasons that we insist on positions having a less than operation or being comparable is because we want to be able to easily, cheaply, and universally bound check slices of collections. And the reason for that is because what you often want to do with a collection is to slice bits of it and send different slices to different threads and have them write only to their section of a vector or whatever the object is. So I don't know if that's what the commentator was referring to, but that was my goal with this being able to have bounds check slices, was definitely thinking about passing different slices to different threads and having them safely be able to write to different parts.
All right, so any final question? Now's your chance. I have two final questions. Yeah, okay. This here?
This is great, by the way. Thank you so much for this. This is.
Do I understand correctly that you need to know the size of your collection beforehand?
You need to be able to check whether you need to be able to provide an end position in constant time. That's not necessarily the same as knowing the size in advance. So no, you can have a collection whose size is not known a priori, right? But you have to be able to provide an end position in constant time. So it sounds a bit weird, but it's possible to have things like a take while adapter that uses a special position type that kind of acts a bit like a sentinel, a bit like common range does if you're familiar with that in the ranges library. So you can have positions whose size is not known in advance, if that's a simple answer to your question. You can't. So collection. The reason, well, going back to the naming of it, collections can't be infinite. Collections have to have a finite size, right? But you don't necessarily. They have to at some point. You will get a position that's equal to the end position. So iterables can be infinite. I cut slides about that, right? Because ranges handles infinite, it really doesn't handle infinite ranges. It's very bad with it. It doesn't have very good support at all. Iterables can be infinite. That's absolutely no problem at all. You just, you just never return iteration result complete, right? You just keep looping until the user breaks out. Really simple. Collections in this model, a collection is always finite, right? It represents some object in memory that you can have repeated access to. That's kind of the idea behind the collection API. A stream is an iterable, but it's not a collection. Yes, hello.
Also, the question you mentioned that the Flux is also compatible with the range-based form, but that again would not give you the optimal performance. You have the iterator-based things again. Do you also have an idea to like improve the range-based form to also work with the internal iteration?
Yes. So that's very well observed. Is that although we can make iterables work with the range-based for loop, because of the way the range-based for loop works, we have to do this stop-start. So it's absolutely correct. In an ideal world, if I were in charge of everything, yes, I would update the range-based for loop to use have some way of using internal iteration. I don't know exactly what that would look like. So Jonathan Mueller and Barry Revzin actually wrote a proposal paper for an internal iteration scheme for the standard library a couple of years ago. They, in fact, proposed changing or an extra expansion for the range-based for loop. That proved to be quite unpopular. People didn't like the idea of messing with the range-based for loop. So whilst I said that I'd love to see the iterable thing in the standard, certainly version 1 of that wouldn't touch the range-based for loop. Because I think that's something people find a bit scary. But in the really long term, if I were in charge of everything, yes, I would I would change that to be able to use the run while, certainly.
One last question from our online viewers. There are in the standard library right now we have these parallel deliverables where you can pass an execution policy and execute it multi-threaded or vectorized. Do you plan to implement something like this for your library as well?
We have the parallel STL, and these algorithms work pretty well in isolation, but you don't have much control over them, and in particular you can't compose them into pipelines, right? So they're really nice when you can use them, but they're not all that flexible. I already mentioned it, answered another question, but the executors library is the future of asynchrony parallel stuff in C++. That is how it is going to work in the future. It's been approved for C++26. We're going to get it in standard libraries hopefully soon. My goal is to have really good integration between Flux and executors. Now, I don't know what that's going to look like right now. But it's something that I definitely want to happen in future.
All right. So, I think there's so many questions that eventually you feel like we should stop. So, thank you very much for this talk.
Oh, it's my